Take a look at these: milk, butter, gelatin, mayonnaise, muddy water, and colored glass. We use them in our day-to-day life. But have you ever wondered about the chemistry hidden in them? These substances are known as colloids in chemistry. Colloids play an important role in interface science and in the fields of energy, food, mineral processing, pharmaceuticals, and environment. Colloids are one of the three major types of mixtures, the other two being solutions and suspensions. The three kinds of mixtures are distinguished by the size of the constituent particles. You already know that solutions are homogeneous systems in which the diameter of the solute is less than 10 to the power minus 9 meters. These particles are not visible to the naked eye. Common salt in water is an example of a true solution. On the other hand, a suspension is a heterogeneous system. The particle size of the molecules in a suspension is more than 10 to the power minus 6 meters. These particles can be seen with the naked eye. Sand in water is an example of a suspension. Colloids are mixtures whose particles are larger than the particles of a solution, but smaller than the particles of a suspension. The suspended particles in a colloid are small enough to settle down due to gravity. Thus, colloids represent an important and a large group of systems intermediate between solutions and suspensions. Therefore, a colloid is a heterogeneous solution in which the particle size ranges from 10 to the power minus 9 to 10 to the power minus 6 meters. These particles are not visible to the naked eye, but can be seen under a microscope. Milk, blood, honey, and starch solution are all colloids. Colloids are also called colloidal dispersions because the colloidal particles are dispersed throughout the mixture. For a colloidal solution, we use the terms dispersed phase and dispersion medium. The phase that is scattered or present in the form of colloidal particles is called the dispersed phase, and the medium in which the colloidal particles are dispersed is called the dispersion medium. For example, in a starch solution, starch represents the dispersed phase, while water represents the dispersion medium. Colloids can be classified on the basis of the physical state of the dispersed phase and the dispersion medium, the nature of interaction between the dispersed phase and dispersion medium, the type of particles of the dispersed phase. Let us first discuss the classification based on the physical state of the dispersed phase and the dispersion medium. Depending upon the physical state of the dispersed phase and dispersion medium, 8 types of colloidal systems are possible. Dispersion of a solid, in a solid, liquid, or gas dispersion mediums result in the formation of a solid sol. fluid sol, and an aerosol respectively. Colored glass and gemstones are examples of solid sols. Paint, muddy water, and cell fluids are fluid sols. Fluid sols are mostly referred to as sols. Examples of aerosols are smoke and dust. Dispersion of a liquid in a solid, liquid, or gas dispersion mediums result in the formation of a gel, emulsion, and an aerosol respectively. Examples of gels are cheese, butter, and jellies. Milk, hair cream, and certain medicines are examples of emulsions. Fog, cloud, mist, and insecticide sprays are examples of aerosols. Dispersion of a gas in a solid or a liquid dispersion medium results in the formation of solid sol and foam respectively. Examples of a solid sol with gas molecules are pumice stone and foam rubber. While soap lather, whipped cream, shaving foam, and froth are examples of foam. It is important to note that the colloidal system of a gas into some other gas is not possible because gases always form a homogeneous solution. Since colloidal systems are heterogeneous, they cannot be obtained by dispersing a gas into another. Depending upon the nature of the dispersion media, sols are given different names. For example, if the dispersion medium is water, then the sol is called as aquasol or hydrosol. And when the dispersion medium is alcohol, it is called an alkosol. Another way of classification is based on the nature of the interaction between the dispersed phase and the dispersion medium. Depending upon the affinity of the dispersed phase for the dispersion medium, colloidal systems can be classified into two categories: lyophilic and lyophobic sols. Let us first discuss lyophilic sols. The word lyophilic means liquid-loving or solvent-loving. When substances like starch, gum, and gelatin are mixed with a suitable liquid, that is, a dispersion medium, they readily form colloidal solutions. Such colloidal solutions are called lyophilic colloids. When water is the dispersion medium, they are called hydrophilic colloids. Lyophilic sols are quite stable and cannot be easily precipitated. An important characteristic of lyophilic colloids is their reversible nature. That is, if the dispersed phase is separated from the dispersion medium, for example, by evaporation, then the sol state can be achieved again by simply mixing with the dispersion medium. Let us now discuss the second category of colloids: lyophobic colloids. The word lyophobic means liquid-hating. Lyophobic colloids cannot be formed by spontaneous dispersion in the medium, but can be prepared only by special methods. Arsenic sulfide, ferric hydroxide, gold, and other metals form lyophobic colloids. These metals are sparingly soluble, and thus their molecules do not pass readily into the colloidal state. Lyophobic colloids are also known as irreversible colloids because the residue obtained by evaporating the dispersion medium cannot be converted back into a sol through ordinary means. Lyophobic colloids are readily precipitated on adding a small amount of electrolyte by heating or by shaking vigorously, and hence are not stable. Lyophobic sols need a stabilizing agent if they are to be kept for longer times. You already know two ways of classification of colloids. Another third method of classification is based on how different substances that form a colloidal solution acquire the required particle size. Accordingly, colloidal solutions are classified into following three categories. They are multimolecular colloids, macromolecular colloids, associated colloids. Let us first study multimolecular colloids. As the name suggests, multimolecular colloids are formed when a large number of atoms or smaller molecules of the dispersed substance aggregate together to form a species whose size lies in the colloidal range. For example, a gold sol consists of particles of various sizes that are a cluster of several gold atoms. A sulfur sol consists of colloidal particles that are aggregates of S8 molecules. These molecules in the aggregate are held together by van der Waals forces. The other category of colloids is macromolecular colloids. Certain substances, like starch, proteins, and cellulose, have molecules of big size, which lie in the colloidal range. The solutions of these substances in suitable solvents are called macromolecular colloids. Synthetic macromolecules, such as polyethylene, nylon, and polystyrene, also form colloids when dispersed in suitable solvents. Macromolecular colloidal solutions are stable and resemble true solutions in some respects. Now, we will discuss the last category of colloids, namely associated colloids. There are some substances that behave as normal strong electrolytes at low concentration, but behave as colloidal solutions at a higher concentration. The colloidal behavior is due to the formation of aggregates of small particles. Such aggregated particles are called micelles, and the colloid thus formed is called an aggregated or associated colloid. Surface active agents like soaps and detergents are examples of associated colloids. The formation of micelle depends upon two factors: the concentration of the dispersed phase and the temperature. The formation of micelle takes place above a certain concentration called critical micelle concentration or CMC. And above a particular temperature known as craft temperature or TK. Every missile system has a specific value of critical missile concentration. For soaps, the CMC is 10 to the power minus 4 to 10 to the power minus 3 moles per liter. Each missile contains at least 100 molecules. Missiles are generally formed by specific types of molecules that have both lyophilic as well as lyophobic ends. Soaps consist of sodium or potassium salts of higher fatty acids and are represented as RCOO minus Na plus. In soaps, the alkyl group that consists of long carbon chains is lyophobic, while the polar group is lyophilic in nature. Molecules with lyophilic and lyophobic ends are called surface active molecules or surfactant molecules. Let us now discuss the mechanism of missile formation. In sodium stearate, the long hydrocarbon part of stearate radical, that is C17H35, is the lyophobic end, while COO- is the lyophilic end. When the concentration of the solution is below its CMC, sodium stearate behaves as a normal electrolyte and ionizes to give sodium and stearate ions. These stearate ions remain on the surface of water and orient themselves in such a way that the lyophilic end of the COO- dips in water, while the lyophobic part, the C17H35 part, stays away from it. At the critical missile concentration, the polar COO part is pulled into the bulk of the solution. Thus, a cluster is formed with the hydrocarbon chains pointing towards the center of the sphere, and the COO- part oriented outwards on the surface of the sphere. The aggregate thus formed has the dimensions of a colloidal particle and is known as an ionic missile. Detergents like sodium lauryl sulfate undergo missile formation in a similar manner. The cleansing action of soaps is based upon its tendency to undergo missile formation. The stearate ions of soap arrange themselves around an oil droplet in such a way that the hydrophobic part of the stearate ions is directed towards the oil and the hydrophilic part projects outside. The hydrophilic part, being polar, interacts with the water molecules, and the oil droplet is pulled away from the cloth into the water to form an ionic missile. The stearate ions of soap molecules help in making a stable emulsion of oil with water, which is later washed away with the excess of water. A sheath of negative charge is formed around the globules, which prevents them from coming together and forming aggregates. We can also say that soap acts as an emulsifier and helps an emulsion stabilize. Lyophilic salts are readily prepared by mixing the dispersed phase and the dispersion medium. However, lyophobic salts are prepared by special methods, since they have no affinity for the solvent. The methods for the preparation of lyophobic colloids can be broadly classified into two categories: condensation or aggregation methods. Dispersion methods. We will first discuss the condensation or aggregation methods. As the name suggests, in condensation methods, the smaller particles of the dispersed phase aggregate to form larger particles of colloidal dimensions. That is, the constituent particles in true solutions, such as ions or molecules, are allowed to grow in size to particles of colloidal dimensions. The colloidal solutions are obtained by certain chemical reactions, namely double decomposition, oxidation, reduction, and hydrolysis. Let us now discuss some typical reactions for the preparation of salts. Arsenous sulfide salt can be prepared by a double decomposition reaction. Hydrogen sulfide gas is passed through a dilute aqueous solution of arsenous oxide to yield arsenous sulfide salt. A colloidal solution of sulfur can be prepared by oxidizing an aqueous solution of hydrogen sulfide with an oxidizing agent like sulfur dioxide. Salts of gold, silver, and platinum can be obtained by the reduction of dilute solutions of their salts with a suitable reducing agent. For example, gold salt can be obtained by reducing a dilute aqueous solution of its salt with formaldehyde. Another reaction commonly used for the preparation of salts is the hydrolysis of the corresponding chlorides. For example, if a small quantity of ferric chloride is added to boiling water, a ferric hydroxide salt is obtained. Let us now discuss the second category, dispersion methods for the preparation of colloids. As the name suggests, in these methods, bigger particles of a substance, like a suspension, are disintegrated into particles of colloidal dimensions. The two common dispersion methods are electrical dispersion or Bradig's arc method and peptization. Let us discuss electrical dispersion or Bradig's arc method first. This method is commonly used to prepare colloidal solutions of metals such as platinum, silver, and gold. In this method, two electrodes of the metal whose colloidal solution is to be prepared are immersed in the dispersion medium and an electric arc is struck between the electrodes. The intense heat of the arc vaporizes the metal, which gets condensed immediately in the liquid to form a colloidal solution. This method thus involves dispersion as well as condensation. We will now discuss the preparation of salts by the peptization method. Peptization is defined as the process of converting a freshly prepared precipitate into colloidal form by adding a small amount of a suitable electrolyte. The electrolytes used for this purpose are called peptizing agents. This process involves the preferential adsorption of suitable ions from the electrolyte by the particles of the precipitate to form charged species. These charged species repel one another, and as a result, the precipitate disintegrates into colloidal-sized particles. It is important to note that freshly prepared precipitates are preferred because the particles are not firmly attached to each other, and therefore undergo disintegration easily. For example, the addition of ferric chloride to a freshly prepared precipitate of ferric hydroxide converts it into a colloidal solution reddish-brown in color. Here, the ferric ions from ferric chloride get preferentially absorbed by the ferric hydroxide precipitate. The colloidal solutions prepared by the methods we just discussed are generally associated with some soluble impurities and some excess of electrolyte. Though a trace amount of the electrolyte is sometimes essential for the stability of the colloidal solution, an excess of it causes coagulation of the sol. That is why the sols obtained are subjected to purification to get rid of excess electrolyte. The methods commonly employed for the purification of colloidal solutions are dialysis, electrodialysis, and ultrafiltration. Let us discuss these methods one by one. The first method is dialysis. It is defined as a process to remove a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. This method is based on the fact that colloidal particles cannot pass through a parchment or a semi-permeable membrane, but the ions of the electrolyte can. The colloidal solution is taken in a bag of cellophane or parchment, which is suspended in a vessel through which fresh water flows continuously. The impurities slowly diffuse out of the bag, leaving behind a pure colloidal solution. The apparatus used for this purpose is called a dialyzer. A modified form of dialysis is known as electrodialysis. The ordinary dialysis process is a slow process. To hasten the process of purification, dialysis is carried out by applying an electric field. In this process, 2 electrodes are placed in the water compartment as shown here. When an electric field is applied across the electrodes, the ions of the electrolyte present as the impurity diffuse towards the oppositely charged electrodes at a faster rate. An important application of dialysis is in artificial kidney machines, where it is used to cleanse the blood of patients whose kidneys have failed. Let us now discuss the third method for the purification of colloids: ultrafiltration. It is important to note that colloidal particles can pass through ordinary filter paper because the pores in the filter paper are bigger than the colloidal particles. The separation of a solute from a colloidal system can be carried out by using an ultrafilter, which has smaller pores than an ordinary filter. Ultrafiltration is defined as the process of separating the colloidal particles from the solvent and the soluble solutes from the colloidal solution by specially prepared filters, which are permeable to all substances except the colloidal particles. The size of the pores in the filter paper can be decreased by soaking it in a solution of gelatin or colloidion, followed by hardening with formaldehyde. Usually a colloidion solution is a 4% solution of nitrocellulose in a mixture of alcohol and ether. The filter paper thus formed is known as an ultrafilter and prevents the colloidal particles from passing through it. Ultrafiltration, however, is a slow process. It can be speeded up by applying suction or pressure. To get a pure colloidal solution, the colloidal particles left on the ultrafilter paper are stirred with a fresh dispersion medium. The properties exhibited by colloidal solutions can be classified as colligative properties, optical properties, mechanical properties, and electrical properties. Let us first discuss their colligative properties. Colloidal solutions exhibit the colligative properties osmotic pressure, elevation in boiling point, depression in freezing point, and relative lowering of vapor pressure, in the same way as true solutions do. However, the magnitudes of these properties for colloidal solutions are much smaller than those obtained for true solutions, and thus it becomes very difficult to measure them accurately. This is because colloidal particles, being bigger aggregates, have very high average molecular masses. Therefore, the number of particles in a colloidal solution is small as compared to that of a true solution. Hence, at a given concentration, the value of any colligative property of a colloidal solution is of a small order as compared to the value shown by a true solution. However, colloids exhibit measurable osmotic pressure, which can be determined with a reasonable degree of accuracy. This property of colloidal solutions is therefore used to determine the average molecular masses of certain colloidal particles, like proteins and other polymers. One property of colloids that distinguishes them from true solutions is the Tyndall effect. When a beam of light passes through a true solution, there is no scattering and the path of light cannot be traced. The solution appears clear if observed in the direction of light, and perfectly dark if observed from a direction perpendicular to the direction of light. On the other hand, when a beam of light is allowed to pass through a colloid, it gets scattered by the colloidal particles, and the path of the light can be traced. The path of light gets illuminated with a blush light. This phenomenon of scattering of light by colloidal particles is called the Tyndall effect. The illuminated, bright cone of light is called the Tyndall cone. Try to recollect that every time you go to a cinema hall, you're able to trace the path of the light beam from the projector. what you actually see is the Tyndall effect. A Tyndall cone formed due to the scattering of light by dust particles is seen in the movie hall. The Tyndall effect is observed only when two conditions are satisfied. First, the diameter of the particles of the dispersed phase should not be too small than the wavelength of the light used. This implies that this effect is observed when the dimensions of the colloidal particles are comparable to the wavelength of the visible light used. Secondly, the refractive indices of the dispersed phase and the dispersion medium should differ greatly in magnitude. The Tyndall effect was used to devise an instrument known as the ultramicroscope by Zsigmondy in the year 1903. The instrument is used to detect particles of colloidal dimensions. In an ultramicroscope, an intense beam of light is focused on a colloidal solution in a glass vessel. The solution is then observed in the microscope at right angles to the beam of light. The zone of light scattered by each individual colloidal particle is larger than the particle size. Therefore, a colloidal particle appears as a bright star against a dark background in constant motion when viewed through an ultramicroscope. Thus, we can say that the ultramicroscope does not render the actual colloidal particles visible, but allows the light scattered by them to be observed. It does not provide any information about the size and shape of the colloidal particles. The Tyndall effect also confirms the heterogeneous nature of colloidal solutions. Another important optical property of colloids is their color. Colloidal solutions are generally colored. The size, shape, and nature of the particles determine the color of a colloid. Larger particles absorb light of longer wavelength and therefore transmit light of shorter wavelength. For example, in a gold sol, if the particles are very fine, the sol is red in color. But when the size of the particles grow, the color changes to purple, then blue, and finally golden. The color of a sol also depends upon the manner in which the observer receives the light. For example, in reflected light, an aqueous solution of milk appears blue, whereas it looks red in transmitted light. Let us now learn about the mechanical properties of colloidal solutions. The continuous zigzag movement of colloidal particles in a dispersion medium is called Brownian movement. This random zigzag motion was first observed under a powerful microscope by the British botanist Robert Brown, and is named Brownian movement after him. Brownian movement is independent of the nature of the colloidal particles, but depends upon their size and on the viscosity of the solution. The movement of colloidal particles increases with a decrease in their size and in the viscosity of the medium. Brownian movement is caused by the bombardment of the molecules of the dispersion medium against the colloidal particles of the dispersed phase from all sides with unequal and unbalanced forces. This movement opposes the forces of gravity and has a stirring effect, meaning that the colloidal particles resist settling rapidly to the bottom of the vessel. Hence, we say that Brownian movement is responsible for the stability of a colloidal solution. Apart from exhibiting color, the Tyndall effect, Brownian motion, and colligative properties, colloidal solutions also exhibit electrical properties. The properties that we will discuss in this module are electrical charge on colloidal particles, electrophoresis, electroosmosis, and coagulation of salts. Let us first discuss the most important electrical property, the presence of electrical charge. The particles of a colloidal solution possess a definite electrical charge, either positive or negative on them. Due to the presence of the same charge, they repel each other and do not combine to form larger particles. This keeps them dispersed in the medium, and hence, a colloidal solution is stable. All the particles in a solution carry the same charge. The dispersion medium has an equal and opposite charge. Based on the nature of the charge on the colloidal particles, colloidal solutions are classified as positively charged or negatively charged salts. Hydrated metallic oxides like Al2O3, XH2O, Fe2O3, XH2O, and Cr2O3, XH2O, and basic dyes like methylene blue form positively charged salts. Starch sol, metal sols like copper sol and gold sol, metal sulfide sols like arsenious sulfide sol, and acid dyes like Congo red are examples of negatively charged salts. The electrical charge on colloidal particles may be due to several reasons. These include electron capture by the colloidal particles during electrodispersion of metals, preferential adsorption of ions from the solution, and the formation of an electrical. Let us discuss the most accepted reason first, the preferential adsorption of ions. Colloidal particles have the tendency to preferentially adsorb a particular type of ion from the solution. An ionic colloid preferentially adsorbs the ion common to the colloidal particles from the solution. For example, silver iodide precipitate adsorbs iodide ions from the dispersion medium if an excess of potassium iodide is used to prepare it. This results in the formation of a negatively charged colloidal solution. However, if an excess of silver nitrate is used for the precipitation of silver iodide, preferential adsorption of silver ions takes place, resulting in the formation of a positively charged colloidal solution. Similarly, a positive sol of hydrated ferric oxide is formed if ferric chloride is added to excess of hot water. This is due to the preferential adsorption of ferric ions. However, a negatively charged sol of ferric hydroxide is obtained when ferric chloride is added to sodium hydroxide. In this case, there is preferential adsorption of hydroxyl ions on the colloidal particles. In either case, the ions left out will give an equal and opposite charge to the dispersion medium and will remain in it. The positive or negatively charged colloidal particles of a layer attract oppositely charged ions from the dispersion medium, forming a second layer as shown here. These counterions are not absorbed on the surface of the colloidal particles, but exist in the solution. The combination of two layers of opposite charges around a colloidal particle is called the Helmholtz electrical double layer. The first layer is firmly held and is called the fixed layer, while the second or the outer layer is mobile and is termed as the diffused layer. The presence of opposite charges on the fixed and diffused layers of the double layer results in a difference in potential. This potential is called electrokinetic potential or zeta potential. Let us now discuss another electrical property of colloidal solutions, electrophoresis. The movement of colloidal particles towards a particular electrode under the influence of an electrical field is called electrophoresis. Electrophoresis helps establish the existence of electrical charge on colloidal particles. This property can also be used to establish the nature of the charge carried by the colloidal particles in a colloidal dispersion. The direction of movement of colloidal particles towards a particular electrode is governed by the nature of the charge on them. If the colloidal particles carry a positive charge, then they move towards the cathode when subjected to an electrical field, while negatively charged colloidal particles move towards the anode. An important application of electrophoresis is in sewage disposal. Let us discuss another electrical property, electroosmosis. If an electrical field is applied to a colloidal solution and a semi-permeable membrane is used to prevent the colloidal particles from moving, then the dispersion medium moves in a direction opposite to the direction in which the colloidal particles would have otherwise moved. This phenomenon is called electroosmosis. Let's define it. Electroosmosis is the movement of a dispersion medium under the influence of an electrical field when the movement of colloidal particles is prevented by a suitable membrane. Under the influence of an electrical field, the colloidal particles and the dispersion medium both have a tendency to move towards the oppositely charged electrodes. But the semi-permeable membrane does not allow the passage of the colloidal particles. The dispersion medium, however, can pass through the membrane and therefore its movement takes place. Another very important property of colloids is their coagulation, flocculation, or precipitation. You already know that one of the factors responsible for the stability of lyophobic colloids is the presence of charge on colloidal particles. However, if the charge is destroyed, they are free to come near each other to form larger molecules. These larger molecules aggregate or coagulate and then settle down under the force of gravity. This phenomenon is called coagulation or precipitation of the sol. The coagulation of a lyophobic colloidal solution can be achieved in a number of ways. One method is electrophoresis. You know that the colloidal particles in a colloidal dispersion move towards a particular electrode under the influence of an electrical field. If the process is carried over a prolonged period of time, then the colloidal particles get discharged at the oppositely charged electrode and get coagulated. Another method used to bring about coagulation is by mixing two oppositely charged sols. Mixing equal proportions of two oppositely charged sols neutralizes the charges either partially or completely, and thus causes the colloids to coagulate. For example, if equal proportions of a positively charged sol of hydrated ferric oxide and a negatively charged sol of arsenious sulfide are mixed, then the coagulation of both the sols takes place. This type of coagulation is called mutual coagulation. A sol may also be coagulated by simple boiling. When a sol is boiled, the adsorbed layer on the colloidal particles is distributed because of the higher number of collisions with the molecules of the dispersion medium. This reduces the charge on the colloidal particles and ultimately leads to precipitation. Arsenious sulfide sol undergoes coagulation on boiling. The coagulation of a sol can also be brought by persistent dialysis. You already know that traces of electrolytes are essential for the stability of colloids, since they get absorbed on the surface of colloidal particles by giving them charge. If the electrolyte is removed completely by persistent dialysis, then the colloidal solution would become unstable and undergo coagulation. The most important and useful method of coagulating sols is by adding an electrolyte. While traces of electrolytes are essential for stability, adding substantial amounts brings about the precipitation of colloids, as it completely neutralizes the charge on the colloidal particles. The ion responsible for causing coagulation is the one that carries a charge opposite to that present on the colloidal particles, and is known as the coagulating ion. For example, a positively charged sol gets coagulated by the negatively charged ions of the electrolyte that is added. The coagulation behavior of different electrolytes can be explained on the basis of the Hardy-Schulze rule. The rule states that the greater the valence of the flocculating ion added, the greater is its power to cause precipitation. Let's see an example. The coagulating power of different cations to coagulate a negative sol follows the order aluminium 3+ ions greater than barium 2+, greater than sodium+. This shows that tripositive ions are more effective than dipositive and unipositive ions. Similarly, the coagulating power of different anions to coagulate a positively charged sol decreases in the order FeCN6 negative greater than PO4 negative greater than SO4 negative greater than Cl negative. The coagulation of a sol by an electrolyte does not take place until the electrolyte added has a certain minimum concentration in the solution. The minimum concentration of an electrolyte in millimoles per liter required to cause a sol to precipitate in 2 hours is called its coagulating value or flocculation value. It is important to note that the smaller the flocculation value, the greater is the coagulating power of the electrolyte. You can see from the table that the aluminium 3 cation and the FeCN6 negative anion have extremely low values of coagulation power. Therefore, they exhibit greater coagulating capacity as compared to other ions in their category. Lyophilic sols, on the other hand, are much more stable than lyophobic sols and do not get coagulated easily under similar conditions. The two factors responsible for the stability of lyophilic sols are the existence of the same charge on all the colloidal particles and the extensive solvation of the colloidal particles of a lyophilic sol. A lyophilic sol can be coagulated either adding an electrolyte or a suitable solvent. A higher concentration of an electrolyte is needed to coagulate a lyophilic sol than is needed to coagulate a lyophobic sol. When solvents like alcohol or acetone are added to hydrophilic sols, the colloidal particles get dehydrated. Under this condition, a small quantity of electrolyte is able to bring about coagulation of the hydrophilic sol. Let us now discuss the protection of colloids. You already know that lyophobic sols, such as metal sols, are very susceptible to coagulation or precipitation. The process of protecting them from coagulation is referred to as protection of colloids. It has been observed that in the presence of certain lyophilic colloids, lyophobic sols acquire greater stability. They do not get coagulated easily when an electrolyte is added. A layer of lyophilic sol particles around the lyophobic sol particles prevent them from coagulating. The sheath of solvent molecules of the lyophilic colloid prevents the particles of lyophobic colloids from aggregating at low electrolyte concentrations. For example, adding gelatin, a lyophilic colloid, to gold sol, a lyophobic sol, protects the gold sol from getting coagulated if a small amount of sodium chloride solution is added. Emulsions are liquid-liquid colloidal systems in which both the dispersed phase as well as the dispersion medium are liquids. An emulsion may be defined as a colloidal dispersion of two immiscible or partially immiscible liquids, in which one liquid acts as the dispersion medium and the other as the dispersed phase. In most emulsions, one of the liquid is water, while the other is a hydrocarbon and is referred to as oil. Depending on the nature of the dispersed phase, emulsions are broadly classified into two types. They are oil and water type emulsions and water and oil type emulsions. In oil and water type of emulsions, oil acts as the dispersed phase and water acts as the dispersion medium. For example, milk is an emulsion of liquid fat globules dispersed in water. Another well-known example is that of vanishing cream. In water and oil type of emulsions, water acts as the dispersed phase and oil acts as the dispersion medium. For example, butter is an emulsion of water dispersed in fat. Other common examples of this type are cod liver oil and cold cream. Emulsions are generally unstable and separate in two layers on standing. Thus, to stabilize an emulsion, small quantities of certain other substances called emulsifiers or emulsifying agents are added. Emulsifying agents stabilize an emulsion by reducing the interfacial tension between the two phases. Proteins, gums, natural and synthetic soaps, detergents, etc. are the principal emulsifying agents for oil and water type of emulsions. Similarly, heavy metal salts of fatty acids, long-chain alcohols, lamp black, etc. are used for water and oil type of emulsions. Emulsions exhibit properties similar to colloids, like the Tyndall effect, the Brownian movement, electrophoresis, coagulation or de-emulsification on the addition of electrolytes, and so on. Emulsions can be diluted by adding any amount of the dispersion medium, that is, water for oil in water type emulsion and oil for water in oil type of emulsion. On the other hand, if the dispersed phase is added to an emulsion, it forms a separate layer. An emulsion can be separated into its constituent liquids by boiling, freezing, centrifuging, electrostatic precipitation, etc. A well-known example of centrifuging is the separation of cream from milk. Finally, let's see some important applications of emulsions. A large number of pharmaceuticals in the form of lotions, creams and ointments, which are oil in water or water and oil type of emulsions, are prepared to facilitate easy absorption by the body. The cleansing action of soap is based upon the formation of an oil in water emulsion. The concentration of ore by the froth flotation process is based upon the treatment of the powdered ore with an oil emulsion. Milk which is an important constituent of our diet, is an emulsion of liquid fat droplets in water. The digestion of fats in our body takes place by the process of emulsification. Asphalt, emulsified in water, is used for building roads without the necessity of melting the asphalt. Colloids play a very important role in nature and in our daily life. The food we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read are all largely composed of colloids. Let us now discuss some important applications of colloids in day-to-day life. Have you ever wondered as to why the sky appears blue? The sky is the empty space around the earth and has no color as such. It appears blue due to the scattering of blue light by the dust particles and the water suspended in the air. Seawater also looks blue for the same reason. The colloidal impurities in seawater scatter blue light. The Tyndall effect of scattering of light by colloids is responsible for the blue color of the sky and the seawater. Do you know that some of the food we eat is colloid? Milk, halwa, butter, ice cream, fruit juices, jellies, etc. are colloids in one form or the other. For example, milk is an emulsion of fats in water, while ice cream is a dispersion of colloidal ice particles in cream. Another very important colloidal solution is blood. Bleeding from a fresh cut can be stopped by applying a concentrated solution of ferric chloride or potash alum. The negatively charged colloidal particles of blood get neutralized by the ferric or aluminium 3+ ions, resulting in the coagulation of blood. Fog, mist, and rain are all colloidal in nature. In winter, at night, the moisture in the air condenses on the surface of dust particles, forming tiny droplets. These droplets, being colloidal in nature, float in the air, forming mist or fog. It is interesting to note that even clouds are colloidal systems. Clouds are aerosols consisting of small droplets of water suspended in air. Due to condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. It is worth noting that a natural disaster of cloudburst is believed to occur due to the mutual discharge of oppositely charged cloud particles. A cloudburst results in a very heavy downpour in a short period of time. We also come across the term artificial rain. Clouds, as we now know, are colloidal, carrying some electrical charge. Clouds can be made to cause rain by spraying oppositely charged colloidal dust or sand particles or precipitates of silver iodide over them. The neutralization results in coagulation of the water droplets, which come down in the form of rain. This type of rain is called artificial rain. Another interesting example is the formation of a delta at the mouth of a river, when it meets the sea. River water is a colloidal solution of sand and clay. which carry a negative charge. Seawater contains a number of electrolytes of sodium, magnesium, and calcium. When river water comes in contact with seawater, the positively charged ions of the electrolytes coagulate the negatively charged colloidal particles, which settle down. The level of the riverbed rises, forcing the stream of water to split. This happens again and again, and over time the river takes the shape of a delta. A noteworthy example you are already familiar with is the cleansing action of soaps. Soap solutions are colloidal in nature. They remove the dirt and oil particles either by adsorption or by emulsifying the greasy matter sticking to cloth. Let us now look at some industrial applications of colloids. The most important industrial application of colloids is the Cottrell smoking precipitator. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, and dust. Smoke from industries is a major air pollutant, and therefore it is desirable to precipitate it to prevent it from spreading. The Cottrell precipitator precipitates smoke on the principle of electrophoresis. Smoke is allowed to pass through a chamber with a number of metal plates. These metal plates are attached to a metal wire connected to a source of high potential of about 30,000 volts. The charged particles of smoke get attracted by the oppositely charged electrodes or metal plates and fall to the bottom after getting discharged. The clean hot air passes out through the chimney, thereby reducing pollution. Another important application of coagulation of colloids is the purification of water. Water from natural sources often contain impurities that are colloidal in nature. Precipitating these colloidal impurities can be carried out by adding certain electrolytes like potash alum or aluminium sulfate. The negatively charged colloidal particles of the impurities get coagulated by the action of the aluminium 3+ ions furnished by the electrolyte and settle down. Pure water can then be filtered or decanted off. Yet another application of colloids is in medicines. Colloidal medicines are more easily assimilated by the body system, as they can act over a large surface area. Therefore, they are more effective. It is for this reason that a large number of pharmaceutical preparations are emulsions. For example, milk of magnesia used for stomach disorders. Cod liver oil and skin ointments are all emulsions. Some important salts that are commonly used as medicines are argirols, a silver metal sol used as an eye lotion. Colloidal antimony used for curing chalaza. And colloidal gold used for intramuscular injections. It is important to note that antibiotics are usually injected into the body in colloidal form. Another industrial application is in the leather tanning industry. Raw skin hides of animals contain positively charged colloidal particles. When a hide is soaked in negatively charged tannin and compounds of chromium, mutual coagulation takes place in the pores of the hides. This results in the hardening of the leather. The process is called tanning. The principles of colloids and interface signs are used for the successful formulation and manufacture of photographic products. The color-forming components are usually delivered in colloidal form. Photographic plates and films are prepared by coating an emulsion of light-sensitive silver bromide in gelatin over a glass plate or a celluloid film. Another application of colloidal salts is in the rubber industry. Latex obtained from rubber trees is an emulsion consisting of negatively charged rubber particles in water. Rubber is obtained by the coagulation of latex. This coagulated mass is later subjected to vulcanization and is sold as rubber. We have discussed a number of applications of colloids in life and in industry. Furthermore, inks, paints, lubricants, synthetic plastics, cement, smoke screens are all colloidal solutions. Sewage disposal also makes use of the phenomenon of electrophoresis, as sewage water is colloidal in nature.